In this segment, what we're going to be doing, we're going to be taking a look at the Reynolds number that is defined for condensation on vertical or inclined surfaces. And we'll be using that as we develop some of the correlations in the next lecture. Now, the thing about condensation, when we're looking at heat transfer with condensation, there are many, many different Reynolds numbers that we're going to be looking at, depending upon how you define it. But this is one definition of the Reynolds number. So V is the average velocity of the condensate flowing down the surface. Rho is the density of the liquid. Mu is the dynamic viscosity of the liquid. dH, I'm going to write it up here. This is the hydraulic diameter, and it is defined as being 4 times the cross-sectional area, AC, divided by the perimeter. And that would be the cross-sectional area perpendicular to the direction of which the film is moving, so the velocity, and that's going to depend upon the nature of the shape. There are two areas that we're going to use in condensation, so be very, very careful not to confuse them. We have wetted area, which is the one that we typically use whenever we're using Newton's law of cooling, and that will be A. And then we have this AC, and that is essentially the cross-sectional area perpendicular to the wall or perpendicular to the velocity. So if we look at a surface where we have a film growing like that, this here, if we look, that is typically delta. And let's say this plate is of width B. So I'll say the width is B in this direction. Okay, so there's our film coming down. The film is moving in that direction. AC is essentially this cross-sectional area here, AC, which is going to be, it will be the perimeter times delta, where perimeter, it would be, for a unit length, that would be B. So just to make a comment about that, AC is equal to the perimeter times delta, and delta is the thickness of the film. And the perimeter, for example, if we're looking at a vertical plate, it would be equal to B, as we just put in this drawing. If we're looking at a vertical cylinder, however, it's going to be different. Now with the vertical cylinder, the radius of the cylinder, so that would be there, R needs to be much larger than the thickness of the film of delta. But what will happen is you get condensation forming around, and here the area is going to be related to the perimeter, or the cross-sectional area. So the perimeter, as we've defined, is equal to pi times d, and that would be for a vertical cylinder. Okay, so just be aware that this cross-sectional area, AC, that is different from A, which is wetted area, that we will see in a moment as we look at Newton's law of cooling when we start coming up with the convective heat transfer coefficient. And so you can imagine here this cross-sectional area for a cylinder will be a little bit more complex than it would be just for the plate. But anyways, there are two different areas that we're going to use. Don't get them confused. hopefully I haven't confused you with all of this stuff here. All right, so what we're going to do, we're now going to take a look at a generic plate, a vertical plate, and this is one that is often used when looking at condensation flowing on a surface. And here is our plate. And depending upon the book that you're using, sometimes TS will be the wall temperature, sometimes TW will be the wall temperature. In any event, we're assuming that the gravity vector is going in that direction. And our coordinate system, we will draw y normal to the plate and x in the direction of the plate. And what happens is we begin with a film that might grow something like that. And let me clean that up a little. Okay, so it's coming down, and then it goes into a wavy regime, and then eventually it becomes turbulent. And so depending upon the Reynolds number, we're actually in different regimes here, and so we will be denoting those in a moment. Before I do that, however, I want to put in a few other variables that are within this. On the outside of the film, we will call that the saturation temperature. And then further out here, we have the vapor. And so you could have a scenario where it's superheated vapor and it's above the saturation temperature, or you could have it at the saturation temperature. Usually we assume it to be at the saturation temperature, but in the event that it's higher, I will denote it with TV free stream. And so here, what is happening is we have mass flow rate of condensate moving down. And as the film gets thicker and thicker, the mass flow rate is going to increase because we keep adding more and more fluid as we have more fluid condensing. And so m dot is going to be a function of x. And the other thing that we have here, we typically define delta as being the thickness of our layer, and consequently we know that delta is a function of x. And the other thing that we did, and I defined this in the Reynolds number that I just presented a moment ago, with the Reynolds number I said that there was some average or bulk velocity. In reality there's going to be a velocity profile here, but for right now what we're going to do is assume that we have some bulk velocity of the condensate moving down due to the body force or gravity. So if we were to look at this, what we have up at the top, this would be where we have Reynolds number approximately equal to 0. And in this region here, we refer to it as being laminar, and it's also called wave free. Then when you get to a Reynolds number of approximately 30, what happens is you get laminar, but it is wavy. And so those waves would be instability waves developing within the fluid, the film itself. And instability waves grow, and it's the process of transition from laminar to turbulent, but it is characterized by waves that we would see on the surface. And that will exist until we get to a Reynolds number of about 1800. And once we get to a Reynolds number of 1800, then our film becomes turbulent. And just like with when we looked at the flat plate boundary layer or a lot of the other things we've been doing in this course, whenever you transition from one regime to another, your correlations are going to change. And so we will see that when we look at the experimental correlations that have been collected for the condensation on a vertical surface or plate like we're looking at here. So I think that's the majority of the things that I wanted to write. It is. Okay, so now what we do, I want to define a Reynolds number, and we looked at Reynolds number a moment ago, but I'm going to basically massage that Reynolds number, and we're going to come up with different Reynolds numbers, which you'll find is quite common when you're looking at condensation. And We're going to begin by looking at a definition for the mass flow rate. And so we can say the mass flow rate is going to be equal to the density of the liquid in the film. And it's going to be equal to, it will be rho AV. And so the A here is going to be, remember the cross-sectional area. That is going to be, for example, if you have a vertical plate, that's going to be delta times B, where B would be the width of the plate. And that will also be multiplied by capital V, which is the bulk velocity of the fluid going through. So we're going to take that mass flow rate and we're going to use it in a definition of the Reynolds number. Because if you look back, when we had Reynolds number here, we have some of those components there. We have rho and we have V, and the cross-sectional area is embedded within the hydraulic diameter, which we can pull in. So it's going to enable us to be able to recast the Reynolds number in terms of the mass flow rate.